Burn like a pro.
Ever wonder how we shoot information across the globe at light speed through these tiny glass threads? Or how about this, how your car just knows when it starts to rain? Well, believe it or not, it all boils down to one simple idea: bending light. So let's jump right in and see how this one little change in direction unlocks some seriously amazing tech.
All right, to really get a feel for this, let's start with something we can all picture. Imagine you're driving, cruising along on a nice paved road. Suddenly, your right side wheels hit a big patch of mud. What happens next? The whole car kind of lurches and swerves, right? It gets pulled right into that mud. Well, that simple, everyday skid, that's the perfect way to understand exactly what happens to a beam of light. And here's the why. It's all about speed. The wheels in the mud slow way down, but the wheels still on the pavement are going full speed. And that massive difference in speed is what forces the car to pivot, to turn. Well, guess what? Light does the exact same thing. When it's traveling through one thing, say air, and then suddenly hits another, like glass, its speed changes. And that change in speed is what makes it bend.
Okay, so this bending action, it actually has a name. It's the cornerstone of everything we're going to talk about today. We call it refraction. So what is refraction? It's really just a fancy word for the bending of light. That's it. It happens anytime light passes from one transparent thing to another, like from air into water or from water into glass. And the reason why it happens is always the same. The light changes speed. Now we have a way to describe how much a material slows down light. We call it optical density. And it's actually pretty simple. In a less dense medium, like air or a vacuum, light just zips along at top speed. But the moment it hits something optically denser, think water or even a diamond, it gets bogged down. It slows down. The rule is easy. The denser the material, the slower the light. All right, so we know light bends, but how does it bend? Is it just random? No way. Physics is all about rules, and this is no exception. There are super clear, predictable rules that govern exactly how it bends. So let's get into them. Okay, check this out. This diagram breaks down the two big rules of the bend. First thing you see is that dotted line. We call that the normal. It's just an imaginary line drawn at a perfect 90-degree angle to the surface. So here's rule number one. When light enters a denser medium, it slows down and bends towards the normal. And rule two is just the opposite. When light leaves a denser medium and goes into a less dense one, it speeds up and bends away from the normal. Towards and away. It's really that straightforward. Now, to put some numbers on this, physicists came up with something called the refractive index. We just use the letter N for short. Honestly, you can just think of it as a light bending score for any given material. The higher that score, the more that material grabs onto light, slows it down, and bends it. So how do we find this N value? Well, there are two main ways. The first formula is all about speed. It just compares the top speed of light in a vacuum, which we call c, to its slower speed inside the material, v. The second one, which has the cool name Snell's law, is more about the geometry of it all. It basically proves that for any two materials, there's this fixed, predictable relationship between the angle the light hits at and the angle it bends to. Let's look at some real-world examples to see what this means. Air has a refractive index of pretty much just 1. It hardly bends light at all. Water is about 1.33. Glass is around 1.5. But then you get to diamond, holy cow, its index is a massive 2.4. And that's the secret to why diamonds sparkle like they do. That huge score means they are ridiculously good at bending light, making it bounce around inside like crazy before it escapes. Okay, so we know how light bends. We've got the rules, we've got the numbers, but what if we keep pushing it? What if we try to bend it more? Is there a limit? Oh yeah, there is. And when you hit that limit, something totally different and pretty spectacular happens. This is where we get to the tipping point. This limit has a name. It's called the critical angle, and it is a very, very specific angle. If you're shining a light from a denser material into a less dense one, and you hit the surface at exactly this critical angle, the light doesn't actually escape. It bends so dramatically that it ends up just skimming right along the surface, perfectly flat at a 90-degree angle. And you can see it perfectly right here. The light comes up from the denser stuff below, it hits the boundary at that magic critical angle C, and boom, the exiting ray just travels right along the edge. It's like it's teetering on a razor's edge, right between escaping and not. So what do you think happens if we push that angle? Just a tiny bit more. Well, this is the big reveal. The second you push that incoming angle even a tiny bit past the critical angle, the light just gives up trying to escape. It stops bending out altogether. Instead, it does a complete 180 and reflects perfectly back down into the material it started in. This is total internal reflection, or TIR for short. The light is officially trapped. Now, to make TIR happen, there are two rules you absolutely cannot break. They are non-negotiable. First, the light has to be going from a denser medium towards a less dense one. You can't do it the other way around. And second, that angle it hits the surface with, the angle of incidence, it must be bigger than the critical angle. You meet those two conditions, you get TIR every time. Let's walk through this step by step. So here in the first panel, the angle is less than the critical angle. And what happens? The light just bends and escapes. Normal, everyday refraction. Nothing special yet. Then, in the second panel, we hit the critical angle exactly, and there it is, that tipping point. The light bends so hard it just skims right along the boundary line. And finally, the third panel. We've pushed the angle just past that critical point. And look, the light is completely reflected back down. The boundary has basically turned into a perfect mirror. The light is trapped.
So we can trap light. That's awesome. But this isn't just some cool party trick for physicists. This is the engine, the fundamental principle behind some of the most important technologies we use every single day.
Let's kick things off with the internet. You've heard of fiber optics, right? Well, those are just super thin strands of glass. We take our data, our movies, our messages, everything, and turn it into pulses of light. We shoot those pulses into the fiber at just the right angle, an angle greater than the critical angle. So as that light zips down the fiber, every time it hits the wall, it doesn't escape. It undergoes total internal reflection. It just bounces and bounces and bounces its way for miles, with practically no loss of signal. It's amazing.
Okay, how about getting a better view of things? You know, in really high-end binoculars or cameras, they often don't even use mirrors to steer the light. They use prisms. And you might ask, why? Well, even the best mirror absorbs a tiny bit of light, which makes the final image just a little bit dimmer. But a reflection from TIR? It's literally 100% efficient. Zero light is lost. That means you get a much brighter, crisper image, and the whole thing is way more durable. And finally, let's go back to that car we started with, that clever rain sensor. Here's how it works. There's a little device on your windshield that shoots a beam of infrared light at the glass from the inside. When the glass is dry, the light hits the outer surface. And, you guessed it, total internal reflection happens. The beam bounces back to a detector. But the moment a raindrop lands on that exact spot, everything changes. The light is no longer trying to escape from dense glass into less dense air. Now it's trying to go from dense glass into slightly less dense water. And that change is enough to break the condition for TIR. The light escapes into the raindrop, the detector sees the signal suddenly disappear, and bam, it tells your wipers to turn on. It's just genius in its simplicity.
Wow, okay. We have covered a ton of ground here, from a simple bend all the way to trapping light. So let's pull it all together into one simple cheat sheet. And here it is. The whole story in one place. You've got the basic rules of refraction up top, then the formulas we use to calculate it. Over here is our tipping point, the critical angle. And finally, the two non-negotiable rules for total internal reflection, which is what unlocks all that amazing tech. You can see how it all flows together, from a simple bend to a perfect trap.
You know, we started this journey with a car skidding in the mud, and we ended up with the technology that runs the modern internet. Just by understanding one fundamental rule of physics, we figured out how to trap light itself. It really makes you wonder, doesn't it? What other fundamental rules are out there just waiting for us to figure them out? And what will we learn how to trap next?